What's up, guys? In this video we're going to be talking about a new type of segment and line in a circle called a secant line, and we're also going to learn about some theorems as well. So going over this definition, a secant line passes through a circle twice. So if you guys take a look at this example of a secant line, we can see our secant line is in yellow, and it's touching the circle at two distinct points, and it's cutting right through them. So it's not just stopping at A and B, but it's continuing through on both ends. Okay? So there are a lot of different examples of secant lines that we can draw. We can draw a secant line going really in any direction and in any spot of the circle. So I can draw a secant line that looks like this, right? And again, we're passing through the circle at two distinct points and we're continuing on, right? So a secant line should not just be inside of a circle, it has to be both inside and outside. We can draw multiple secant lines in the same diagram too. I can draw another secant line that looks like this, and we're still touching at two distinct points, right? We can even have examples of our secant lines touching the same point at the end over here. But again, the whole definition needs to be, I am touching my circle at two distinct points. So let's relate this to some of our other vocabulary that we've learned about. So chords are kind of similar to secants in a way, because remember that a chord is a segment that connects any 2 points on a circle. But the difference between chord and a secant is that a chord, yes, we're connecting 2 distinct points, but we're stopping right there. We are not continuing outside of the circle, and that is the main difference between a chord and a secant. So a chord is only inside of a circle, but a secant is cutting from the outside of the circle and it's going right through it. Now, we also have that a tangent line touches a circle once at the point of tangency and creates a 90-degree angle with the radius or diameter. Now, we can see our tangent line over here in blue. It's touching our circle once, and we know that there's no radius drawn right now, but we know that if we did draw one to this point of tangency over here, that these angles must be 90 degrees, just by definition. And then now we have our new vocabulary word of secant line, which we can see in red in this diagram. Now this vocabulary is really important to start to commit to memory, make some flashcards, because we're going to need to be able to identify a bunch of different segments when our diagrams get a bit more complex. So let's get right into our secant theorem. So for secant lines, similar to tangents, we evaluated when tangents were drawn from a common point, and we're going to talk about when secants are drawn from a common point. So that common point is going to be external here. So in this case, we have two secant lines. We have secant MO and MQ, and they are both being drawn from point M. So these are the types of examples we're going to examine. Now our diagrams might look complex, or the secant lines might be drawn in a different spot. Like for example, if I draw secant lines going this way, right? But the idea is we're evaluating them when they're drawn, when they meet at the same external point. So theorem number 1 is talking about finding segment lengths when our secants are meeting at an external point. So a refresher over here, we did this with tangents as well. And when tangents were drawn from that same external point, we knew that these segments here were going to be congruent, right? Now, when two secant lines are drawn from the same external point, we have this equation that's going to be made. So our secants are not congruent, but the product of the whole and exterior are going to be equal. So we can see that our whole, and the formula you're going to remember, it sounds silly, but it helps me remember it, is we equals we, or we, right? Like French, right? WE equals WE. That's a super important formula we're going to need. But you got to know what the letters mean, right? So W stands for the whole secant. So our whole secant is this entire line right here in green, times the external portion. The external portion is just what's on the outside. Then we move over to our other secant line. Now we have our other whole secant line in orange over here, times its external piece, which is just in blue. All right, let's get right into an example using this theorem. So we have in the diagram below, secant, CBA, and CED intersect at C. So right away, I'm boxing this word secant. It's going to be important to us. And we have that AC is 12, BC is 3, and DC equals 9. Find EC. So let's go ahead and label. So they first give us that the entire value of AC, right, that's this entire secant line or segment, is 12. It also gives us that BC, which if you notice, BC is just the external part of our secant. BC is 3. It gives us that DC is 9, and DC is the entire value of the other secant, and it wants us to find EC. Now, EC is this external portion of our secant, right? So whatever we're looking for, we're going to put X there. And again, I have two secants that are intersecting, and I'm looking for a segment value. So that's a dead giveaway that we can go ahead and actually apply this theorem. Now, what this theorem says, you got to remember the equation. When you have two intersecting secant lines, you just write WE, WE equals WE. Now, what that means is whole times external equals whole times external. So the whole value of our first secant line is 12. So we do 12 times the external portion, which is 3, equals the whole other secant line, which is 9, times the external portion of that secant line, which is X. So I color-coded it just exactly how this is color-coded over here. So our whole is in green, our external piece is in red, our other whole is orange, and the other external is blue. So we go ahead and solve this. We get 36 equals 9x. And when we divide by 9, we get 4 equals x. So what that tells me is that EC is equal to 4. Now, always go back and double check. There might be times where you need to substitute this x in elsewhere, but in this case, we were good. So again, when you have two intersecting secants, or two secants in general, we, okay? Now, theorem number 2 is going to be talking about, we're still going to have secants drawn from the same point, but now we're going to be talking about how to find those angles and those arc measures. So refresher, we did this for tangent lines already. So this external angle when we had tangents was equal to half of the major arc minus the minor arc. Now, this external angle theorem is actually the same for any line that you have, but in this case, specific to secants, when two secant lines are drawn from the same external point, that external angle is equal to half of the difference of the intercepted arc. So it's the same exact thing as when we have tangent lines. This external angle theorem applies for every single external angle that's created. So in this case, though, you want to make sure that you're highlighting your angle. So in this case, our external angle is X right there. So we want to make sure that we highlight our entire angle, because that's going to help us see the arcs that we're intersecting. So when you want to see the arcs that you're intersecting, you highlight your angle, you mark the points that your angle's touching, right? So here I know that this arc is definitely involved, but then there are two other points on the circle that are angles touching, and that's these 2 points right here. So this is the other arc that's going to be involved. So another way that I like to write this, I'll just do x, which is our external angle is equal to half of the major arc minus the minor arc. And another way you can remember this is that x equals 1/2 of big minus small. So we're trying to come up with easier ways to remember the formulas. When we're doing segments, it's we. And for this one, I just like to remember 1/2 of big minus small. So let's get right into an example here. So in the diagram below of circle O, PAC and PBD are secants. Again, them being secants is super important. If it said that they were something else, this theorem might not apply, right? So it says if the measure of arc CD is 70, so let's go ahead and label that. Arc CD is 70, and the measure of arc AB over here is 20, and it wants us to find the measure of angle P. Now, angle P is that external angle, right? So, again, I always like to rewrite our formulas out. External angle equals 1/2 of big minus small. Now, our external angle is what we're looking for. That is what we should put as x in our diagram. So, x equals 1/2 of our big arc, the major arc, is 70 degrees, minus the small arc, the minor arc, which is 20. So, we get x equals 1/2 of 50. And that's going to give us that x equals 25. Now let's go back. Do we need to substitute it in anywhere? We do not. So angle P equals 25. Okay. Now there might be examples where you actually have the external angle and you need to find one of the arcs. But again, just write your formula out, substitute what you have, and solve for your missing piece. All right, last but not least, now we're combining something. So we did our secant theorems, but theorem number 3 is going to be when we have a secant line and a tangent line in the same example. So when a secant line and a tangent line are drawn from the same external point, so you can see that over here we're meeting at this external point over here, it says the product of the secant and its exterior is equal to the value of the tangent squared. So before, when we had two secants, we did we, right? Now, when we have a secant and a tangent, it's going to be we equals tan squared. So WE equals tan squared. And what that stands for is that the whole secant the whole secant times its external piece is equal to the value of the entire tangent line or tangent segment squared, right? Now, a good way to remember this, like, you can't use this whole times external if you don't have a secant line, though, because your tangent lines don't have, like, the whole entire tangent line is also the external piece, right? So if you're using whole times external, that has to be your secant line. So let's just dig right into an example. So in the accompanying diagram, PA is tangent to circle O, and PBC is a secant line. So whenever you see tangent and secant in the same word in the same question, it is likely that you are using this formula, y equals tan squared. Okay? Let's go ahead and fill in what we have. So we have PB is 4, so that is nicely filled in for us. We have that BC, which is this piece over here, is 8, and it wants the length of PA. So PA is this tangent portion over here. So let's get right into it. So our whole entire secant line, when we combine that, it's going to give us 12. So the whole secant, we have 12 times the external piece, which is over here, that's 4, equals, PA is what we're looking for. So we should put PA as x in our diagram, and that's going to be the value of our tangent portion squared. So x squared. So we get 48 equals x squared. And then what we need to do, you take square root. So radical 48 equals x. And for that, I don't have, we could do it in simplest radical form, but for this case, that's not what this question's testing. So we get that PA equals the square root, of 48. All right, so to summarize, we have 3 different theorems and concepts that we're working with throughout this lesson. So when we have secant lines that are drawn to the same point, remember the formula we need is we, where we have whole times external equals whole times external. Then we have exterior angle theorem for secants, right? Where we have our exterior angle equals 1/2 of big minus small, and that's talking about the arcs, right? And then last but not least, that last formula when we have a secant and tangent is y equals tan squared. Okay, so make sure you know these 3 formulas. You're not going to get them on your reference sheet, but easy ways to remember them. y equals tan squared, and then this exterior angle formula is going to apply for every single lesson, so we'll get better with it with practice. So again, when you're reading your questions, annotate, figure out what segments you have. Are you looking for segments? Are you looking for angles? Do you have a tangent involved? And it will help you figure out the theorem to apply.